a typical situation that we would see in a building where we've got cold on one side.
Excuse me.
We've got cold on one side, warm on the other side. This could be an air-conditioned environment. It could be a cold winter environment. What we're doing in this situation is trying to show the application of insulation. We would put insulation in place to insulate the cold out or insulate the cold in. Now, one of the enemies of insulation's purpose is to provide resistance to heat loss. So what we're trying to do, provide resistance to heat loss, is trying to keep the heat or the cool of the energy inside the building. So in this situation, what we're worried about is we're worried about when we create conductivity in insulation, where we put moisture in and actually cause the energy loss to occur when we're trying to stop energy loss.
Okay.
So in this situation, what we're concerned about is we're concerned about moisture. Moisture exists in all environments in the form of humidity, so we're trying to stop that humidity from condensing and driving through a system. So what we're going to show here is that in this situation, because we have a cold on one side, warm on the other side, Mother Nature's very powerful and she wants to just create a situation where everybody's equal. We have more humidity on a relative side on one side than on the other. So we end up with condensation moisture drive. So if we looked at this meter and I'm checking the moisture content of the wood, the moisture is actually starting to become encased in the wood, so we're getting a rating of 13 inside the wood. Now, that's because we don't have insulation here, but if we had insulation in place, what we would do is we would actually prevent some of that by warming up that dew point temperature and not getting it. So we would take something like a polyiso, which is used a lot in the business, and we also supply polyisos, and we would say, okay, that doesn't have moisture content. Okay, that's good because now that's going to give me resistance to energy loss. So this is just a piece of insulation that's sitting here. Now, if I put it in our application, though, what we see happening, though, is that some of that condensation is occurring in our insulation. Right. Now, what I'm doing is I'm putting a vehicle in there for energy loss because I'm putting a conductor in there. That's because I'm pushing too hard on it. Come on, do it again. What did I do? Did I break my meter? So you can see what we're doing is we've got moisture pickup in the system. Sure. So that's concerning us because what's going to happen is the effectiveness of this insulation is now going to be diminished due to the transportation mechanism of moisture that's allowing the energy to move through.
Okay.
Now, this is a good situation because we're putting insulation in place. Now, we can be better. We should strive for something better. That's what extruded. The difference between the two insulation is one will pick up moisture, the other will not. So when we're looking in life, we all have choices. When we look at good, better, best, we lead with extruded for the reason that it's really adverse to moisture. It will not pick up moisture. Dow has been putting extruded in PMR roofs, which is a roof that the water basically and the insulation sit together in a protected membrane roof, like garden roof assemblies. We put this in because of it's really adverse to moisture, will not pick up moisture. And so therefore this becomes more effective in application. In certain environments, what we're going to do in the severe north where we've got a bigger delta, what we do to stop that drive is we'd start putting polyethylene vapor retarders or bituminous vapor retarders in place to stop that drive.
Okay.
What all I'm illustrating here is that the damage moisture can cause in certain products versus other products.